Right now, as you read this, 3 independent systems are approaching failure thresholds across North America. An atmospheric circulation pattern that hasn't collapsed this severely in 4 decades is dumping Arctic air across regions with no infrastructure to handle it. Roads are locking under ice accumulation, measured in inches, not fractions. Power grids designed for moderate winter load are about to face demand spikes they were never built to sustain. Families in cities that consider 20 degrees cold are preparing for wind chills approaching -40. This is not weather. This is a stress test of every assumption we made about what winter means below the 45th parallel. Stay with me until the end, because what separates this event from every cold snap you've lived through is not intensity alone, but the convergence of mechanisms that should not be operating simultaneously. By the end, you'll understand why meteorologists who have spent 30 years forecasting winter are using words like unprecedented without exaggeration. Over 150 million people are currently inside the impact radius of Winter Storm Fern. That number represents nearly half the population of the United States. 35 states have activated emergency operations centers. Schools across the South and Midwest canceled classes 3 days in advance, something that does not happen for ordinary winter weather. Airlines preemptively grounded thousands of flights, not because runways were already closed, but because they knew those runways would become unusable and aircraft would be stranded. Hardware chains in Dallas and Atlanta, cities where snow shovels are novelty items, reported total depletion of generator inventory and pipe insulation stock within 48 hours of the first forecasts. This is not precaution. This is recognition that the event unfolding has already exceeded the bounds of manageable disruption. The meteorological map, currently displayed across every forecast center in the country, shows a system so geographically vast, it requires zooming out to continental scale to capture its full extent. From the Canadian border to the Florida Panhandle, from the Front Range of the Rockies to the Appalachian Ridgeline, a single coherent atmospheric structure is controlling temperature, precipitation, and wind. Winter Storm Fern is not a localized blizzard. It is a hemisphere-scale reorganization of where cold air is allowed to exist. The storm has mass. It has momentum. It has a structure that satellite imagery reveals in stark clarity, a vortex of cloud moisture wrapping counterclockwise around a core of Arctic air that has no business being this far south, this late in January. What makes this different from the cold snaps you remember is not just the temperature anomaly. It is the combination of temperature and moisture. Arctic air by itself is manageable. Dry cold can be endured. But when that air collides with moisture streaming in from the Pacific and the Gulf of Mexico, the physics changes. You get phase transitions. Water, vapor, condenses. Rain freezes on contact. Snowflakes aggregate into dense, heavy structures that accumulate faster than removal systems can respond. The result is not snow you can shovel or cold you can dress for. The result is ice accumulation that brings down transmission infrastructure and freezing rain that turns every surface into a mobility hazard. The wind chill projections for the upper Midwest are entering the domain where human tissue damage occurs in minutes. -40 to -50 degrees Fahrenheit wind chill is not an inconvenience. It is a physiological timer. Exposed skin begins freezing within 5 minutes. Respiratory tracts constrict. Fingers lose dexterity. Vehicles refuse to start because engine oil thickens beyond the capacity of starters to turn crankshafts. These are conditions that most Americans under the age of 50 have never experienced and do not know how to navigate. The last time wind chills of this magnitude reached this far south was January 1985, an event still cited in climatology papers as a reference case for polar vortex disruption. Forecast models are converging on ice accumulation totals that power utilities classify as catastrophic. 1 inch of ice on a power line does not bend the line. It snaps it. The weight exceeds the tensile strength of the cable and the structural load capacity of the poles. When that happens across hundreds of miles of distribution networks simultaneously, restoration is not a matter of hours. It is a matter of days or weeks, depending on crew availability and road access. In regions where temperatures remain below freezing throughout that restoration period, the secondary impacts begin. Pipes burst in homes without heat. Water distribution systems fail. Shelters reach capacity. Hospitals activate surge protocols. This is not hypothetical. Oklahoma and Texas grid operators are already coordinating mutual aid agreements and prepositioning repair crews because they know what is coming. The economic impact of this storm will be measured in tens of billions of dollars. Lost productivity as entire metro areas shut down for multiple days. Emergency response costs as state and federal resources are mobilized. Infrastructure, repairs, roads, bridges, and utilities sustain damage that will take months to fully address. Agricultural losses as livestock and crops are exposed to temperatures they cannot survive. But the number that matters more than economic output is the human cost. People will die in this storm. They die in car accidents on ice-covered highways. They die from carbon monoxide poisoning when they use generators indoors. They die from exposure when they lose power and have no backup heat source. Every major winter storm produces fatalities. This one will produce more because it is reaching populations that are not adapted to this level of cold. What makes this moment particularly unsettling is not just the severity of the current event, but what it represents in a larger pattern. For years, climate scientists have been warning that Arctic amplification, the fact that the Arctic is warming faster than the rest of the planet, leads to a weaker temperature gradient between the pole and mid-latitudes. That weaker gradient destabilizes the jet stream, the boundary current that normally keeps cold air contained in the north. A destabilized jet stream meanders. It develops large amplitude waves. And when those waves dip southward, they create pathways for Arctic air to flood into regions unprepared for it. What we are seeing this week is not an anomaly. It is a preview, a demonstration of what winter looks like when the atmospheric circulation patterns that govern the 20th century no longer hold. Because the cold itself is only the delivery mechanism, we have to look at what happens when that air mass collides with infrastructure designed for a different climate. The United States power grid was not built for simultaneous extreme cold across multiple regions. Grid operators plan for peak demand based on historical data. They model winter load using decades of temperature records that tell them how cold it typically gets and for how long. Those models are about to be invalidated. The demand spike coming over the next 72 hours will exceed planning assumptions in multiple grid regions simultaneously. And when demand exceeds supply in an electrical grid, the system does not gracefully degrade. It fails in cascade. Texas learned this lesson in February 2021, when a similar polar vortex disruption sent temperatures plummeting and demand soaring. Natural gas wells froze. Power plants went offline. The grid operator implemented rolling blackouts that were supposed to last minutes, but stretched into days. People died. The economic damage exceeded $100 billion. In the aftermath, there were promises of weatherization and grid hardening. Some improvements were made, but the fundamental vulnerability remains. When you have a grid designed for a summer peak load and you hit it with winter demand that exceeds summer peaks, while simultaneously losing generation capacity because plants cannot operate in extreme cold, you get failure. Oklahoma and Arkansas are in a similar position. Their grids are summer peaking systems optimized for air conditioning load, not heating. Natural gas infrastructure in these states includes wells, processing plants, and pipelines that have minimal cold weather protection because historically it has not been needed. But when temperatures drop below -10 and stay there for days, equipment fails. Wellheads freeze. Compressors shut down. Gas pressure drops. Power plants that depend on that gas supply lose fuel. Wind turbines, which provide a significant fraction of generation capacity in Oklahoma, ice up and stop turning. Solar panels, already less effective in winter, get covered in snow and ice. The dispatchable generation that remains cannot cover the gap. Further north, the Midwest grid faces a different problem. The region is accustomed to cold, but not this cold, and not with this much precipitation. Ice storms are the nemesis of overhead transmission lines. A 1/4 inch of radial ice accumulation on a conductor increases its weight dramatically. Add wind, which is forecasted to gust above 40 miles per hour across much of the region, and the lines begin to gallop. They swing in oscillating patterns that create mechanical stress at every attachment point. Insulators crack. Crossarms break. Poles snap at the base. When a transmission line goes down, it does not just cut power to the immediate area. It changes load flow across the entire regional network, forcing current through alternate paths that may not be rated for that load. Circuit breakers trip. Transformers overheat. What begins as a localized failure propagates. The transportation network is failing in parallel. Interstate highways across the plains and Midwest are already being closed in segments as visibility drops to zero. In blowing snow and ice makes travel impossible. Departments of transportation have mobilized every available plow truck and salt spreader. But there is a limit to what those resources can do when snow is falling at 2 to 3 inches per hour and temperatures are too cold for salt to be effective. Below about 15 degrees Fahrenheit, rock salt stops melting ice. You need chemical additives or mechanical removal, and mechanical removal cannot keep pace with accumulation rates this high. Commercial trucking is grinding to a halt. The just-in-time logistics system that keeps American shelves stocked depends on uninterrupted highway access. When trucks cannot move, supply chains seize at a guy. Grocery stores in affected regions are already seeing runs on bread, milk, and canned goods. Not because there is a food shortage, but because the distribution network is about to go offline for days. Pharmacies are facing similar issues. Medications that need to be refrigerated or frozen require cold chain logistics that become difficult to maintain when trucks are stranded and warehouses lose power. Hospitals are implementing conservation protocols, rationing supplies they know will not be replenished until roads reopen. Air travel has essentially ceased across the central United States. Chicago O'Hare, one of the busiest airports in the world, suspended operations entirely for 36 hours, something that happens maybe once a decade. Minneapolis, Denver, Kansas City, St. Louis, all either closed or operating at minimal capacity. The ripple effects extend nationwide. Crews are out of position. Aircraft are stranded. Passengers are stuck. Airlines are canceling flights on the East Coast, not because of weather there, but because the planes and pilots are trapped in the Midwest. The hub and spoke system that makes modern air travel efficient also makes it fragile. Disrupt the hubs and the entire network collapses. Water systems are entering crisis mode in regions where sustained subfreezing temperatures are rare. Water mains buried at shallow depth because frost penetration normally does not reach them are now freezing and rupturing. When a main breaks under a road in summer, it is an inconvenience. When it breaks in -20-degree weather, the water flooding the surface freezes instantly, creating an ice dam that makes repair access nearly impossible. Municipal water systems are asking residents to drip faucets to keep water moving through pipes, but that increases demand at a time when treatment plants are struggling to maintain pressure. Some smaller communities are already issuing boil water notices, not because of contamination, but because pressure dropped low enough that the system lost its sanitary seal. Emergency services are being overwhelmed. Fire departments are responding to structure fires caused by space heaters and fireplaces being used by people who lost power. But response times are doubled or tripled because roads are impassable and equipment is having trouble operating in extreme cold. Ladder trucks use hydraulic systems that thicken in cold. Water in hoses and pumps freezes. Firefighters, wearing heavy protective gear in -30 wind chills, face severe physiological stress. EMS crews are running continuous calls for carbon monoxide poisoning, cold exposure, and vehicle accidents. Hospitals in rural areas are going on diversion, telling ambulances to go elsewhere because they are at capacity. But there is nowhere else to go because every facility in the region is in the same situation. The failure is not in one system. It is across all systems simultaneously. Power, transportation, water, emergency services, supply chains, all hitting their limits at the same moment. This is what makes the next 10 days a crisis rather than an inconvenience. When multiple infrastructure systems fail together, they create dependencies that prevent recovery. You cannot restore power without road access. You cannot clear roads without fuel. You cannot deliver fuel without power to run pumps. You cannot keep people safe without power, water, and transportation. The systems are coupled, and right now they are failing in a coupled cascade that feeds on itself. Because infrastructure is failing not from poor design, but from conditions outside its design envelope, we have to look at what is driving those conditions. The polar vortex is the mechanism. Understanding it is not optional if we want to understand why this is happening, and whether it will happen again. The polar vortex is a persistent feature of atmospheric circulation, a belt of strong westerly winds encircling the Arctic in the stratosphere. During winter, when the polar regions receive little to no sunlight, temperatures in the stratosphere above the Arctic drop dramatically. That cold air sinks, creating a region of low pressure. The rotation of the Earth and the temperature gradient between the pole and mid-latitudes generate winds that flow around that low pressure center. Those winds, the polar vortex, act as a containment system. They keep the coldest air locked over the Arctic. Most winters, the vortex remains strong and stable. The jet stream at lower altitudes, which is related to but distinct from the stratospheric polar vortex, maintains a relatively zonal flow from west to east. Cold air stays in the Arctic. Mild air stays at mid-latitudes. Winter weather in the United States and Europe is variable, but within predictable bounds. But every so often, the vortex weakens. The winds slow down. The circulation becomes distorted. And when that happens, the cold air that was contained spills out. What triggers a polar vortex disruption is a phenomenon called sudden stratospheric warming. The name is descriptive. Temperatures in the stratosphere over the Arctic increase rapidly, sometimes by 50 to 90 degrees Fahrenheit in less than a week. This seems counterintuitive. How does the stratosphere warm suddenly in the middle of winter when there is no sunlight? The answer involves wave dynamics. Large-scale atmospheric waves generated in the troposphere by airflow over mountains, by temperature contrasts between land and ocean, and by convection in the tropics propagate upward into the stratosphere. These waves carry energy and momentum. When they break, like ocean waves breaking on a shore, they deposit that momentum into the stratospheric flow, decelerating the westerly winds of the polar vortex. As the winds weaken, the cold pool of air over the Arctic is no longer held in place. It begins to wander. In some cases, the vortex splits into two separate circulation centers. In other cases, it is displaced off the pole, pushed southward into Siberia or Canada. Once the stratospheric vortex is disrupted, the effects propagate downward over the course of 1 to 3 weeks, reaching the troposphere where weather happens. The jet stream, which normally separates cold Arctic air from warmer air to the south, becomes highly amplified. It develops deep troughs and ridges. A trough is a southward dip in the jet stream, a pathway for cold air to flood south. A ridge is a northward bulge, a pathway for warm air to move north. Right now, there is a deep trough extending from central Canada down through the central United States. That trough is a highway for Arctic air. The sudden stratospheric warming that initiated this event occurred in early January. Stratospheric temperatures over the Arctic spiked by more than 90 degrees between January 4th and January 8th. The polar vortex weakened and elongated. By mid-January, it had split into two lobes, one over Siberia and one over Canada. The Canadian lobe sagged southward, dragged by the distorted jet stream pattern. By January 20th, the coldest air from that lobe was pouring into the United States. This is textbook polar vortex disruption. The sequence of events matches what we saw in 1985, and again in 2014. But the intensity this time appears to be greater. What makes this event particularly severe is the depth of the cold pool. Meteorologists measure this using geopotential height fields, which indicate how high you have to go in the atmosphere to reach a given pressure level. When heights are low, it means the atmosphere is cold and dense. When heights are high, it means the atmosphere is warm and less dense. The 500 millibar height field, a standard level meteorologists use, shows anomalies over the central United States that are 3 to 4 standard deviations below normal. In plain language, the air mass sitting over the central U.S. right now is colder than 99% of historical observations for this time of year. Computer models that simulate atmospheric behavior predicted this event about 2 weeks in advance. That is actually impressive. Polar vortex disruptions are difficult to forecast because they depend on the precise timing and amplitude of wave activity propagating into the stratosphere, and those waves are influenced by weather patterns all over the globe. Small errors in initial conditions can lead to large errors in predictions of stratospheric behavior. But in this case, the models were consistent. They showed the stratospheric warming. They showed the vortex splitting. They showed the cold outbreak. Forecasters had time to issue warnings and coordinate preparations. That lead time is why emergency declarations were issued days in advance. It is also why, despite the severity of this event, the death toll will be lower than it would have been without warning. But here is the limitation. Models can predict that a polar vortex disruption will occur, and roughly when the cold air will arrive. What they struggle with is predicting the exact intensity and duration. How cold will it get? How long will it last? Those details depend on factors that are hard to model accurately. The interaction between the stratospheric circulation and the tropospheric jet stream is not perfectly understood. The role of sea ice extent, ocean temperatures, and tropical weather patterns in modulating polar vortex behavior is still being researched. This means forecasts carry uncertainty. The range of possible outcomes a week ago included everything from a strong but manageable cold snap to the historic event we are now experiencing. As the event approached, the uncertainty narrowed. But even now, forecasters cannot tell you with certainty when the pattern will break down and temperatures will moderate. There is also a growing body of research suggesting that polar vortex disruptions may be becoming more frequent. The mechanism is complex and debated, but the basic idea is that as the Arctic warms due to climate change, the temperature gradient between the Arctic and mid-latitudes decreases. A weaker gradient means a weaker jet stream and a weaker stratospheric polar vortex. A weaker vortex is more susceptible to disruption by wave activity. The result is a more meandering jet stream and more frequent incursions of Arctic air into mid-latitudes. At the same time, a warmer atmosphere holds more moisture, which means that when cold air does arrive, it can produce more intense snowfall and ice accumulation. The overall climate is warming, but individual winter storms can become more extreme. This is not settled science. There are climatologists who argue that the evidence for increased polar vortex disruptions is weak, or that other factors are more important. But what is not debatable is that the event happening right now fits the pattern that theory predicts. Rapid Arctic warming, sudden stratospheric warming, vortex split, historic cold outbreak. Whether this becomes the new normal or remains a rare event is a question that will be answered over the next decade as we accumulate more data. But for the people living through the next 10 days, the theoretical debate is irrelevant. The cold is real. The impacts are real. And the mechanisms that produce them are operating exactly as physics says they should. Because cold air alone does not create the disaster we are witnessing. We have to look at the second component, moisture. The collision between Arctic air and moisture is what transforms a cold outbreak into a paralyzing winter storm. And right now, that collision is happening across a front stretching from Texas to Maine. Moisture is being drawn into the system from two primary sources, the Pacific Ocean and the Gulf of Mexico. Each is contributing in a different way, and the combination is catastrophic. From the Pacific, an atmospheric river is aimed at the western United States. Atmospheric rivers are narrow corridors of concentrated water vapor transport, typically a few hundred miles wide and over 1,000 miles long. They form in the subtropics, where warm ocean temperatures generate high evaporation rates, and they are steered by the jet stream. Satellite imagery shows a continuous plume of moisture extending from near Hawaii across the Pacific to the California coast. The integrated water vapor content in this plume exceeds 2 inches, meaning if you could condense all the water vapor in a column of atmosphere, you would get over 2 inches of liquid water. This is an enormous amount of moisture. When that moisture hits the Sierra Nevada and the coastal ranges, it is forced upward. Rising air cools. Water vapor condenses and falls as rain at lower elevations and snow at higher elevations. This is normal. California depends on atmospheric rivers for much of its annual precipitation. But this week, the jet stream pattern is unusual. Instead of the moisture being wrung out entirely over the mountains, a portion of it is being advected inland, carried eastward over the Rockies, and into the Great Plains. Normally, air that crosses the Rockies is dry because it has lost its moisture on the windward side. But when an atmospheric river is strong enough, some moisture survives the crossing. That moisture is now streaming into the central United States. At the same time, southerly winds ahead of the Arctic cold front are pulling moisture northward from the Gulf of Mexico. The Gulf is warmer than average for January, with sea surface temperatures running 1 to 2 degrees above the climatological mean. Warmer water means higher evaporation rates. The air moving north out of the Gulf is laden with moisture, carrying dew points in the 50s and 60s. Values more typical of spring than midwinter. This warm, moist air is surging northward through Texas, Oklahoma, Arkansas, and into the Mississippi and Ohio valleys. When warm, moist air overruns cold air at the surface, the physics gets dangerous. The warm air is less dense, so it rises over the cold air. As it rises and cools, the moisture condenses. If the surface temperature is below freezing, you get snow. But if there is a layer of warm air aloft, above the freezing level, precipitation falls as rain through that warm layer. Then, if there is a shallow layer of subfreezing air near the surface, those raindrops pass through it and become supercooled. They are still liquid, but their temperature is below 32 degrees Fahrenheit. When supercooled drops hit any surface, trees, power lines, roads, vehicles, they freeze instantly on contact. This is freezing rain, and it is the most destructive form of winter precipitation. Ice accumulation is being forecast at levels that are difficult to comprehend if you have not experienced an ice storm. A quarter inch of radial ice, meaning ice coating all sides of an object, is enough to bring down tree branches and cause scattered power outages. Half an inch causes widespread damage. 3/4 of an inch is catastrophic. 1 inch, which is the forecast for parts of Arkansas, Tennessee, and Kentucky, is beyond catastrophic. It is infrastructure destroying. Power lines that are rated to handle a certain amount of ice load, typically 1/4 to half an inch, cannot support an inch. The weight is too much. The lines sag until they touch tree branches or the ground, causing shorts and sparking fires. Or they simply snap under the load. Transmission towers, designed to withstand high winds and normal ice loads, can buckle when ice accumulation exceeds design limits. On the northern edge of the storm, where temperatures are well below freezing throughout the entire atmospheric column, the precipitation is falling as snow. But this is not light, fluffy snow. It is heavy, wet snow with high liquid equivalent. Snowfall rates are exceeding 2 inches per hour in some areas. Winds are gusting to 50 miles per hour, creating blizzard conditions with near-zero visibility. Snow drifts are forming that are 6 to 8 feet deep in exposed areas. Roads are becoming impassable not because they are not being plowed, but because the rate of accumulation exceeds the rate of removal, and drifting is burying the roads as fast as they are cleared. The moisture dynamics are being amplified by the temperature contrast. The greater the temperature difference between the warm, moist air aloft and the cold air at the surface, the more vigorous the precipitation. Right now, that temperature contrast is extreme. Surface temperatures in Oklahoma are in the single digits. Temperatures at 5,000 feet are in the 40s. That 30-degree temperature difference over a few thousand feet of altitude creates instability. Air parcels rise rapidly. Condensation occurs explosively. Precipitation rates spike. This is why radar is showing snowfall rates of 3 inches per hour in some locations, rates you typically see only in the most intense lake effect snowbands or nor'easters. The duration of the precipitation is another compounding factor. This is not a fast-moving system. The storm complex is moving slowly eastward, meaning precipitation will continue in some areas for 3 to 4 days. Snowfall totals are not just about intensity, but about duration. 2 inches per hour for 4 hours gives you 8 inches. 2 inches per hour for 48 hours gives you 4 feet. Several locations in the Central Plains and Midwest are forecast to receive snowfall totals exceeding 30 inches. That is a winter's worth of snow in 2 days. As the system shifts eastward, It will interact with moisture from the Atlantic Ocean, creating a secondary coastal storm. This phase of the event will bring heavy snow to the mid-Atlantic and Northeast. The exact track of the coastal low will determine who gets snow and who gets rain, but the models are increasingly converging on a track that favors heavy snow for interior areas and a mix of snow, sleet, and freezing rain for coastal regions. Major cities, including Washington, Philadelphia, New York, and Boston, are all in the potential impact zone. If the coastal low intensifies rapidly, as some models suggest it will, this phase could become a historic nor'easter in its own right. The moisture feeding all of this is not coincidental. It is a function of a warmer atmosphere holding more water vapor. The Clausius-Clapeyron equation tells us that for every degree Celsius of warming, the atmosphere can hold about 7% more moisture. Global average temperatures are roughly 1.2 degrees Celsius above pre-industrial levels. That means the atmosphere is holding about 8% more moisture than it did a century ago. When a storm system taps into that moisture, it produces heavier precipitation. Winter storms in a warming world can be more intense, not despite warming, but because of it. This is one of those uncomfortable paradoxes of climate change that is difficult to communicate, but is supported by physics and observations. Because three major events are unfolding within the same week, we have to address the question everyone is asking: are they connected? A historic winter storm driven by polar vortex collapse. A severe geomagnetic storm triggered by a solar eruption. An earthquake swarm in Southern California, near the San Andreas Fault. The timing is striking, and human brains are wired to look for patterns and assign causation. So let us be clear about what we know and what we do not know. There is no established scientific mechanism linking solar activity to surface weather. Solar flares and coronal mass ejections emit electromagnetic radiation and charged particles that interact with Earth's magnetosphere and ionosphere, the upper layers of the atmosphere above 50 miles altitude. Those interactions produce geomagnetic storms, auroras, and disruptions to radio communications and satellite operations. But they do not change atmospheric pressure systems, temperature gradients, or moisture transport at the surface where weather occurs. The energy involved in a geomagnetic storm is large, but it is deposited in the magnetosphere and ionosphere, not in the troposphere. The troposphere, where weather happens, is driven by solar heating of the surface, the rotation of the Earth, and the distribution of land, ocean, and ice. Geomagnetic storms do not alter those drivers in any measurable way. Similarly, there is no established mechanism linking solar activity or atmospheric weather patterns to earthquake activity. Earthquakes are driven by tectonic stress, accumulation and release in the Earth's crust, processes that operate on timescales of decades to centuries. The energy involved in moving tectonic plates comes from the Earth's interior, from radioactive decay and residual heat from the planet's formation. Solar radiation and space weather do not influence tectonic stress. The correlation between the solar flare on January 18th, the geomagnetic storm on January 20th, the winter storm on January 22nd, and the earthquake swarm on January 24th is almost certainly coincidence. But, and this needs to be stated carefully, the absence of a known mechanism does not mean we understand everything. Science advances by exploring the boundaries of our knowledge, by asking questions about phenomena we cannot yet explain. There are observations in the scientific literature that hint at possible connections, even if those connections are not understood or widely accepted. Speculation, not fact. Some researchers have investigated whether geomagnetic activity can influence atmospheric electric fields. The Earth has a natural electric field, the fair weather field, that exists between the ionosphere and the surface. During geomagnetic storms, currents in the ionosphere can change, potentially altering that electric field. Could those changes, subtle as they are, influence cloud microphysics or aerosol behavior in ways that affect precipitation? The evidence is weak and contested, but the question is not absurd. Similarly, some studies have looked at whether changes in galactic cosmic ray flux, which is modulated by solar activity, can influence cloud formation by affecting the ionization rate in the atmosphere. Again, the evidence is inconclusive, but the hypothesis is testable. Regarding earthquakes, There are researchers who have explored whether atmospheric pressure changes during storms can influence seismic activity by changing the load on the Earth's crust. The pressure change associated with a winter storm is on the order of a few percent of atmospheric pressure, which translates to a stress change of a few kilopascals. That is tiny compared to the tectonic stresses that drive earthquakes, which are measured in tens of megapascals. But in a fault system that is already very close to failure, could a tiny stress perturbation be enough to trigger a slip? Most seismologists are skeptical, but there are documented cases of reservoir-induced seismicity and injection-induced seismicity, where small stress changes do trigger earthquakes. The question is whether natural atmospheric or hydrological loading can do the same. What is not speculation is that human perception of coincidence is biased. We notice when multiple unusual events occur close together in time, but we do not notice all the times when they do not. If the solar flare had occurred in December and the winter storm in February, no one would be talking about a connection. The timing is striking because our brains are pattern recognition engines that evolved to detect threats, even when those threats are not causally related. This does not mean people are foolish for asking the question. It means we have to be disciplined about distinguishing correlation from causation, and about recognizing when our intuition is leading us into patterns that do not exist. What we do know, with high confidence, is that each of these events is individually explicable within the framework of established science. The polar vortex disruption was caused by a sudden stratospheric warming, a well-documented phenomenon. The geomagnetic storm was caused by a coronal mass ejection from the sun, something that happens regularly during solar maximum. The earthquake swarm is occurring in one of the most seismically active regions on Earth, where swarms have been observed many times before. None of these events required an external trigger. They are all natural variability within their respective systems. But natural variability can cluster. And when it does, the consequences can be worse than the sum of the parts. Even if the solar storm did not cause the winter storm, both are happening at the same time, and both are creating challenges. Satellites and power grids are dealing with space weather impacts while also dealing with extreme cold and ice. Emergency responders are managing winter storm impacts while also worrying about GPS reliability and communication disruptions. The fact that multiple stressors are active simultaneously makes the overall situation more fragile, even if the stressors are independent. This is worth keeping in mind because as the planet continues to warm and as solar cycle 25 continues to ramp up, we are going to see more instances of multiple extreme events occurring close together in time. The question is not whether the events are causally linked, but whether we are prepared to manage multiple crises at once. Because the ground is shaking while the atmosphere and magnetosphere are in turmoil, we have to examine the earthquake swarm in Southern California independently, without assuming a causal link to the other events. Over the past 72 hours, seismologists have recorded more than 400 earthquakes in the Coachella Valley, clustered near the towns of Indio and Thousand Palms. The largest so far was a magnitude 4.9 that struck early on January 24th. That is strong enough to wake people from sleep, knock objects off shelves, and cause minor damage to older structures. But the concern is not the 4.9. The concern is what the swarm might represent. Earthquake swarms differ from typical main shock-aftershock sequences. In a typical sequence, there is a clear main shock, the largest earthquake, followed by aftershocks that decay in frequency and magnitude over time, according to well-known statistical laws. Swarms do not follow that pattern. In a swarm, there is no clear main shock. Earthquakes of similar magnitude occur over hours, days, or weeks, with no obvious temporal decay. This makes swarms difficult to interpret. Are they relieving stress, making a larger earthquake less likely? Or are they loading stress onto a nearby fault segment, making the larger earthquake more likely? Seismologists cannot answer that question with certainty. The Coachella Valley sits in a geologically complex region. The southern San Andreas Fault lies to the west. The San Jacinto Fault runs through the valley. A network of smaller faults threads through the area, many of them not well mapped because they have not produced significant historical earthquakes. The tectonic setting is one of strike-slip faulting, where the Pacific Plate is sliding horizontally past the North American Plate at a rate of about 46 millimeters per year. That motion is not smooth. Faults lock, stress builds, and eventually a fault slips in an earthquake. Swarms in this region are not unprecedented. There was a notable swarm in the Brawley seismic zone in 2012 that included thousands of small earthquakes over several weeks, with the largest reaching magnitude 5.4. That swarm eventually quieted without producing a major earthquake. But not all swarms end benignly. In some cases, a swarm is a foreshock sequence, a prelude to a larger event. The problem is that foreshock sequences are only identifiable in hindsight. Before the main shock occurs, a foreshock sequence looks identical to a swarm. The southern San Andreas Fault, the segment running from the Salton Sea northward through the San Gorgonio Pass, has not ruptured in a major earthquake since 1680, over 340 years ago. Paleoseismic studies, which involve digging trenches across faults and dating past earthquake horizons, suggest that the average recurrence interval for major earthquakes on this segment is about 150 to 200 years. The southern San Andreas is overdue by any statistical measure. When it does rupture, it will produce an earthquake of magnitude 7.5 or larger, with catastrophic consequences for Southern California. Current monitoring capabilities include GPS networks that measure ground deformation, seismometers that detect earthquakes, and INSAR satellite measurements that can detect millimeter-scale surface movements. None of these technologies can predict earthquakes in the sense of specifying when and where a large earthquake will occur. What they can do is detect changes in the rate or style of seismicity that might indicate increased probability. The swarm currently underway is one such change. The rate of earthquakes in the Coachella Valley is elevated compared to background levels. Whether that elevation persists and whether it migrates toward the San Andreas Fault are being monitored closely. There are hypotheses about what drives swarms. One is fluid movement. Water, magma, or other fluids moving through the crust can change pore pressure, reducing the effective stress on a fault and making it easier to slip. The Salton Trough, which includes the Coachella Valley, is a geologically young rift zone with active geothermal systems. Fluids are present. Another hypothesis is a seismic slip, slow movement on a fault that does not produce earthquakes, but changes the stress on nearby faults that do. A seismic slip is difficult to detect because it does not generate seismic waves, but GPS and INSAR can sometimes measure the surface deformation it causes. What scientists cannot do is predict whether this swarm will culminate in a larger earthquake. The probability of a magnitude 5 or greater earthquake in the region over the next week is elevated compared to background, but elevated probability does not mean certainty. Most swarms do not produce large earthquakes, but the stakes are high enough that preparation is warranted. California has earthquake early warning systems that can provide seconds to tens of seconds of warning before shaking arrives. Building codes are designed to withstand strong shaking. Emergency response networks are trained. But even with all that preparation, a magnitude 7 or larger earthquake on the southern San Andreas would cause extensive damage, hundreds of billions of dollars in economic losses, and potentially thousands of casualties. The timing of the swarm, coinciding with the winter storm and geomagnetic storm, is almost certainly coincidental. But it adds to the sense that January 2026 is a month when multiple systems are reaching stress thresholds simultaneously. Whether those systems are causally linked or not, the result is the same. A convergence of challenges that test our preparedness and resilience. What the next 10 days will reveal is not whether nature is predictable, but whether we are adaptable. The polar vortex disruption, the geomagnetic storm, and the earthquake swarm are each individually within the bounds of known natural variability. Together, they create a scenario that is statistically rare, but not impossible. And rare events, by definition, are the ones we are least prepared for. The limits of prediction are now exposed. We can forecast a polar vortex disruption a week or two in advance, but we cannot predict its exact intensity or duration. We can detect a coronal mass ejection and estimate when it will arrive, but we cannot predict the orientation of its magnetic field until it is an hour away. We can monitor earthquake swarms and calculate changing probabilities, but we cannot predict whether a swarm will produce a major earthquake. These are not failures of science. They are the nature of complex systems. The atmosphere, The sun and the Earth's crust are chaotic, nonlinear, and sensitive to initial conditions. Perfect prediction is not possible. What is possible is preparation. Winter storms can be survived if people have heat, food, and water. Power grids can be hardened against both extreme cold and geomagnetic storms. Buildings can be designed to withstand earthquakes. The question is whether we are willing to invest in that preparation when the events we are preparing for are rare. The economic calculation is difficult. Hardening infrastructure is expensive. The benefits are only realized when the extreme event occurs, which might be decades away. But as we are seeing this week, when extreme events do occur, the cost of not being prepared is measured in lives and trillions of dollars. There is also the question of whether extreme events are becoming more frequent. For winter storms driven by polar vortex disruptions, the evidence is suggestive but not conclusive. Arctic amplification is real. The jet stream is changing. But the link between those changes and the frequency of extreme cold outbreaks is still being researched. For geomagnetic storms, the frequency is tied to the solar cycle, which is predictable over the 11-year cycle, but has longer-term variability that is not well understood. For earthquakes, the frequency is determined by tectonic processes that are essentially constant over human timescales. What is changing is not the frequency of the hazards, but our exposure and vulnerability. More people live in earthquake-prone regions. More of our infrastructure depends on electricity and communication networks that are vulnerable to space weather. More of our supply chains are optimized for efficiency rather than resilience. The lesson from January 2026 is not that the sky is falling. It is that the systems we depend on, infrastructure, supply chains, emergency response, have failure modes that we do not fully test until an extreme event occurs. And when multiple systems are stressed simultaneously, the failures cascade in ways that are difficult to anticipate. The power grid fails, which means water systems fail, which means hospitals cannot operate, which means emergency response is degraded, which means recovery is slower, which means economic damage is greater. These cascades are not hypothetical. They are happening right now. What remains unresolved is whether this event represents a threshold. Is January 2026 an outlier, a confluence of rare events that we will not see again for decades? Or is it a signal that the statistical distributions governing these events are shifting, that what was once a 1 in 50-year event is now a 1 in 10-year event? The answer will only become clear over the next decade as we accumulate more data. But waiting for certainty is not an option when the cost of being wrong is measured in lives. The next 10 days will test every assumption we have made about resilience. Families will be without power and life-threatening cold. Highways will be impassable. Hospitals will operate on backup systems. Emergency responders will work around the clock. And when it is over, when the cold finally retreats and the power is restored and the roads are cleared, we will conduct after-action reviews and write reports and make recommendations. Some of those recommendations will be implemented. Most will not, because the memory of crisis fades and the pressure to return to normal is strong. But the systems that failed this week will fail again. The polar vortex will disrupt again. The sun will erupt again. The San Andreas will rupture eventually. The question we face is not whether we can prevent these events. We cannot. The question is whether we can build systems that fail gracefully, that degrade without collapsing, that allow us to maintain safety and basic services even when the extreme occurs. That is the challenge, and it is one we have not yet met.